Okay, good morning, everybody. Welcome to Physics 1510. Can you all hear me? Yes? Okay, good. Thank you. We're typically not going to have your webcams on during these classes just to reduce bandwidth, but to start with, I'd just like everybody to turn their webcams on for a minute so we can just see who we all are. It's we're all going to be in this together, working together in various ways. I'm delighted to see you all and to start a new semester here. This is if you don't have a webcam, please try to get one and email me if that's going to be a problem. We will need to be able to work in small groups in lab and recitation and talk to each other, and that only works well if people can see each other. A lesson I learned last semester when we tried to do this. This remote modality can work fairly well, but it works better if we are able to collaborate and we kind of know and trust each other and can talk to each other. So we'll have to work on that. And one of the ways we'll work on that is to work together in virtual small groups, breakout rooms in Zoom. We'll do some of that in lecture, a lot of it in recitation, in the remote recitation, and labs will run that way too. Physics 1510 is the first semester of the calculus-based physics sequence for science students. This semester, we cover what the physicists call mechanics and thermal physics. What that has to do is making models of physical systems and looking at how interactions between objects affect their behavior, affect their motion, affect their temperature, various things like that. Calculus is required, at least as a co-requisite. And you also are required to take concurrently the lab, which is Physics 1530. If you're not registered for Physics 1530, please do so. This lab is remote, so there's not going to be a limit on getting into it. This lab is very tightly tied to what's going to be happening in lecture, and it'll give you a chance to consolidate, to practice some things, and very importantly, it's going to be an opportunity to work on some computational modeling, which we're going to introduce in lecture. In fact, I'll introduce that today. I noticed that most of you have already signed into Canvas and looked at Canvas. This is great. If you haven't, please do, because the course information, that's going to be your primary venue for course information. The thing called the syllabus has information about the course. It's got information about how grades will be computed. It has a course calendar, which is a little bit subject to revision, but probably pretty good. It tells you when the tests will be. So please get those on your personal calendar now so that we, and it gives you information about how the course will run. I'm not going to go over the syllabus because you can all read, but some of the highlights are there are 3 tests and a final exam. These will be given online through Canvas. There is going to be a weekly quiz, which will be available all day on Thursday. And it will review material. Typically, it will review material on which you've already had homework. Now, this week, there's a quiz on Thursday, but it's not going to count. It's called a practice quiz, although it will review material we do today. But it's partly there so that you can practice using the technology. It requires Respondus, Lockdown Browser, and a webcam. If this is truly impossible for you, please email me and we'll work out some alternative arrangements for this. But this is partly a debugging exercise to make sure we can get through this and see what issues we have with this. Typically there'll be one homework assignment a week. It will be due on Tuesday evenings, and it's best not to do it at the last minute. It will cover the material in the Tuesday and Thursday lectures so that you can actually start working on it right after the Tuesday lecture. The textbook and the homework are online through Wiley Plus. There is a link in Canvas to Wiley Plus, and the ebook is the complete textbook. Okay, so it's there. For your convenience, I've posted reading assignments in Wiley Plus as well, which have just the assigned chapters, the assigned sections of each chapter. But you have access to the whole book, and you can, under Read, Study, and Practice in Wiley Plus, and you can look at all the pieces of the book there. It's a reasonably good ebook. It's reasonably well done, and the homework links to the sections of the ebook. So, and lectures will hit the most important things, but we won't do everything. So you will have to read the textbook. So plan on taking time to do that and do it before you start the homework. I noticed that one person said that they were having problems accessing the textbook. If you want to email me about that, I'll see if I can help with any problems you have. I will have office hours. They'll be virtual. There'll be office hours on Zoom, drop-in things. I'm happy to talk to you at any time if those don't work. So if those aren't convenient for you, you want to have a private conversation, just drop me an email and I'd be happy to set up a time that we can talk on Zoom. The recitation sections in recitation, you'll work together on consolidating what we've been going over in lecture and on some problem solving techniques. The recitations will be, two of them will be conducted in person by James Montano, who's a very good TA. And one is a remote recitation, which I will run on Zoom. And the usual restrictions apply. You have to wear a mask if you're an in-person recitation. You have to maintain distancing. We all want you to stay safe and make it through the semester healthy and still cheerful. Do you have any particular questions about sort of logistics and class structure before we actually start doing some physics? If you do, put them in chat. Yes, recitations start today. So both the on-campus and remote recitation section will happen this afternoon. The labs, Physics 1530, will not start until next week, but you do have you will have a pre-lab assignment. You'll have an assignment after today, and I'll explain more what it is when you have a chance to after we've done a few things. And there will be a pre-lab assignment to work through before the first lab. I do realize that the Monday lab is going to get nuked by Labor Day on the third week, and we'll have to work out a way to work around that. But we'll get that done. How do you know which recitation you should attend? Lectures will be recorded. Thank you for that question. Lectures will be recorded, and I will post links to them in Canvas. Okay, if you have trouble with Wiley Plus, please email me. The way Wiley Plus should work is that you should be able to get into Wiley Plus, see the book and the homework. You have to pay for it. I think it's $69 for a semester. The easiest way to pay is just to pay Wiley online. But you have a couple of weeks of grace period of free access. So you have a little time to do this. Okay, let me remind you again, if you came in a little bit later, please type your name in chat. This is so I can take attendance. And okay, now what I'm going to do is switch to sharing my screen. I'm going to ask you to turn off your webcams. And I'm going to show you a little bit about something that's a little special about this course that we're going to end up doing together. One of the things we're going to do, physics is about making models of the physical world. We use mathematics to do that. We use words, we use diagrams, but we also use computers to make these models come alive. And in this class, we're going to be making computational models, and you're going to learn to do this, to make simple computational models. You don't have to have any computer experience. We'll learn what we need to know together. But this is a really central part, not only of physics, but of the other sciences now. Chemists use computational models all the time to model reactions and conformations of molecules. There are lots of very important models in biology. Mathematicians use computation, so it's a really central piece, and it's a thing that we'll be working on together. Okay. So this is an application on the web just called Glowscript.org, and I'm going to make a new program. So this is, we're going to be working in a language called Python. This is a standard computer language that's used very widely in the sciences and also for data analytics, and some in engineering. A lot of web programs are written in Python also. And we're going to use a special version of it called VPython, which allows us to do interesting graphics and animations. So I'm going to write out my first Python program here. I'm just going to write the word sphere here, and then I'm going to say run this program. And what happens is I get a display that has a ball that looks like a sphere. If I use the right mouse button, I can rotate the camera, and you can see that the light changes as I rotate the camera. So this is a three-dimensional sphere. Now that's not really very interesting, and there's no physics in it. So suppose we say, well, let's move it. Well, how do we say where we want to move it? We live in a three-dimensional world, and so we need to specify a three-dimensional position for this object. So we'll say position is vector. Now, I'm going to be typing some things here that we haven't covered yet, and that's okay. You don't feel anxious about following this. Don't write it down. I just want to show you the kind of thing we can do, and then we're going to be filling in the gaps, the physics and the math, as we go along during the semester. So the position is a vector, and I'm going to move it. It started at the origin by default, but I'm going to move it to -6, 3, 0. We're in a three-dimensional Cartesian coordinate system with the x-axis running to the right, the plus y-axis running up, and the plus z-axis coming out of the screen at you. And we'll make it something other than boring white. And we'll give it a radius of 0.5. Okay, so we're probably working in SI units here, meters, kilograms, seconds. And now we see that it moved. It could plausibly be at -635 if the origin's in the center of the screen. But you see that nothing happens because the computer doesn't know any physics. So any physics that we put into this model, we have to tell it about. So let's give this thing a name. We'll call it ball so we can talk to it. And let's give it a velocity so it can move. So we'll say a velocity is a vector 0.900. And we run the program. That doesn't do anything because the computer doesn't know. Why does it not look like a sphere? It's parallax from the camera. So if I zoom out using the scroll wheel, you can see that it now looks more like a sphere. And if I rotate, we can see it's a sphere. It's just that when we're really close and it's close to us, we're getting some distortion just from the camera lens. And now, so we have to tell the computer how to move it. So we're going to do just what movies do. We're going to take little time steps and replot all the objects in our screen as we take little time steps. So we're going to make a time step delta t of 1/1000th of a second, and we're going to set our time counter to 0. And now we're going to say while the time is less than, let's say, 60 seconds times 60 minutes, so an hour. We're going to say the position of the ball, the new position of the ball, should be set to the old position of the ball plus velocity times delta t. And if we run this program, oh, I spelled it wrong, and so I made my first error here. You'll see error messages frequently, but it's a pretty good error message. It tells me what I spelled wrong. And we better... Okay, so that was my error. I actually made an infinite loop. I forgot to update t. So there we go. Now we didn't see anything. Why? Well, the ball actually moved too fast for us to see. So let's slow it down. We'll tell it not to do this more than 800, update it more than 800 times a second. And now we see our ball moving across the screen. Now this is really pretty boring. We could make it leave a trail. We'll tell it make trail is true. But that's pretty boring, and it's not a model of much of anything except what might happen in outer space. So it would be more interesting if it could do something like bounce. So let's make a floor. We'll make a box. And box and sphere are sort of what we call graphics primitives here. So box has a position. We'll make it 0, -5, 0. Color is color.green. And width is, let's say, 20 meters. Length is 20 meters. And height, let's put this on the next line. Height is not very thick, 0.05 meters, and we'll make it green. We already made it green. All right. Okay, so now we have a floor, and this is starting to look more like a three-dimensional scene, but the ball isn't falling because we didn't tell the computer about any physics. So what we need is a way to put into this program the interaction of the ball with the Earth. Yeah, make the entire solar system would be really cool. So let's say we know that the force the Earth exerts on the ball. Those of you who've taken physics before, this may be familiar. The gravitational field of the Earth near the surface of the Earth is 9.8 newtons per coulomb. And so when you're close to the surface of the Earth, the force on an object near there is fairly constant. The force is the mass of the ball times g. Well, we're getting ahead of ourselves here. The ball needs a mass because force is proportional to mass. So we'll say the mass, m for mass, is 0.2 of a kilogram. And now the force, well, force has a direction and a magnitude, so it's a vector too. So it's a vector. There's a 0 in the x direction. In the negative y direction, it's m times g, and in the z direction, it's 0. Now we put in this force, but again, the computer doesn't know what to do with it, so it's not going to do anything. So we now have to tell the computer how the force affects the motion of the ball. Well, what forces do is forces change momentum. They change the momentum of an object. So what we need to do is specify the momentum of the ball, and the initial momentum, which for some reason that I don't know is usually called P in physics, is approximately equal to the mass of an object times its velocity. And now we're ready to tell it how the force affects it. So what we tell it is that the new momentum of the ball is equal to the current momentum of the ball plus the force acting on it times delta t. And now we get a new velocity. Velocity is going to be the momentum over the mass. And so now the force ought to act on the ball. It's in the negative y direction, so the ball ought to go down. And it does. Well, don't panic because I told you it is getting complicated, but we're now covering material that's several chapters in. Okay, so we're now in chapter 2 here at least. So I'm just kind of showing you what we're doing. We're going to go through this. It could have quantum tunneled through the floor, but it's very likely that we didn't tell the computer about floors. Well, a lot of people are scared by coding, but what I have for you today is an assignment. Welcome to VPython, which is just a chance for you to go home and mess around with this environment. We will teach you the pieces of coding you need, little step by little step. And to some extent, we're going to start out very gently. We'll make models together and you'll modify them. And as you gain these skills, you'll learn to make more and more modifications. So let's just tell it about the floor. So we'll say if the y component of the position of the ball is less than the y component of the position of the floor, it's just going to bounce. So we'll say the y component of momentum switches direction. This is what we call an elastic collision. And now we have a ball running along under the influence of the Earth's gravity, interacting with a floor. We can rotate the scene to see that it's bouncing in a straight line. It looks like we kind of forgot to tell the computer about the extent of the floor. And so the ball is happily doing what we told it to. Well, the interesting thing about computational models, Parker, is that you can add some of these. We could add air resistance, for example, quite simply when we're coding, whereas if trying to solve it analytically with mathematics, it's very tough. So this gives us a really simple way to do this kind of thing. Now, this, of course, is just a model. So what would happen if we reversed the direction of the gravitational force? Either by making a mistake or by just to see what would happen. Now our ball falls up. So computational modeling, let's put it back so it falls down, but computational modeling gives us a chance to experiment with well, but the nice thing about a model is a model can, the physics is what you tell it is. That's right, the ball fell up. So when we make these computational models, we have a chance to explore things that we wouldn't have a chance to explore otherwise. Okay, so that's a quick view of where we're going to get to by the end of the semester. And don't panic, there's a lot of support. There's me and two really excellent TAs, James Montano and Jacob Emmerich, to help you with these things. We'll have very structured things to do, but you'll also have a chance to play around and try some things, to experiment. And to see how physics actually affects the world by writing F equals vector 0 minus m times g 0. That doesn't automatically jump out at most people as making things bounce. So we have a chance to explore physics in a new way. Now, we're going to have plenty of equations. You're missing equations. We'll have lots of equations. No worry. And in fact, there were plenty of equations in that computational model. So let's go back to it. These are all algebraic equations here. So momentum is mass times the vector velocity. V is a vector. The new momentum is the old momentum plus F delta T. That's an equation. So we have lots of equations. In the model, the floor was just, so the graphics, let's go back to that model for a second here. Here. So the statement that just said draw a box to represent the floor, that was just make a box. And what do you have to do to draw a box? Well, you have to tell the computer where to draw the box, how big it is, and what color it is. Now, the part about the floor here that made it bounce was that what we did is we said if the y component of the ball's position, the y coordinate of the ball, was actually less than the y component of the floor's position, which is a really coarse-grained check, okay, because that means the ball has actually gone through the middle of the floor. Then we should reverse the direction of the ball's momentum. So those equations are what we had. What I'd like to show you now is how we describe the world in 3D using vectors. Now, what I usually do when I'm doing this is we bring an object and we make an origin in the classroom and we make measurements from the object to various things. And so what we're going to do here is, so Seth's question, when making something such as a box and giving it a vector location, does the vector enter the centermost point of the box? For many objects, it does. So a sphere, the position is going to be at the center. The box, the position's at the center. For something like a cylinder or an arrow, and we'll see some arrows here, the position is actually going to be at the tail, because that's where it made the most sense. So here is a virtual classroom where we can explore 3D vectors. And so we have a virtual orange instructor, a blackboard, and some carefully socially distanced students. And the students are, so the width of, just for a sense of scale, the width and length of the floor is 10 meters, and all these people are exactly 1.8 meters high. Marco, that's a really good question about why the ball falls down again after a while. And I think by the end of next week, it'll be extremely clear to you why it's happening. What we just did is tell the computer about the physics, and we let the physics go. So that's what happened. So here is our virtual classroom, and in order to make any measurements, to locate anything in it, we're going to need an origin and axes. So we're going to put an origin in the classroom, and that's going to be the yellow ball here. That's going to be our origin. That's 0, 0, 0. We could put it anywhere we wanted to, but that's where it is right now. And we're going to use, it's a Cartesian coordinate system, so we will use axes that reflect the ones we just saw in that computer program. So x goes to the, plus x goes to the right, plus y goes up, and that means that plus z has to come out at you, because this is what we call a right-handed coordinate system. And what that means is that if you take your right hand and you point your thumb in the direction of x with the palm facing toward you, and your first finger in the direction of y, then your second finger should point out toward you in the direction of z. And so that's your right hand. Okay, so now we have the simplest kind of vector. The simplest kind of location is just position. And position in a 3D coordinate system can be represented by a thing called a vector. So we're talking about vectors here. And a vector is any quantity that has both a size, a magnitude, and a direction. And a position vector is a vector that goes from an origin to some location. So let's make that a little bigger here. So let's see if we can draw some arrows representing vectors, position vectors here. So let's draw an arrow that starts at the origin and it goes to this orange instructor here. Okay, so here's our arrow going from the origin to the instructor. I picked the tops of people's heads as the location because that way we could see the tips of the arrows. And the computer obligingly tells us that the tail of the red arrow is at 0, 0, 0, which is our origin. But the vector from there to the tip, extending from the tail to the tip, is -2, -7, -1.5. Now, does that make sense? Let's see. So it's going in the negative x direction because the instructor is over on the negative x side of the axis. It's going in the negative y direction because the instructor's head is actually lower than the origin. And it's going in the negative z direction because the instructor is actually behind the origin. So that's a position vector. It has units of meters. Okay. So let's draw another position vector. Let's start at the origin and draw an arrow to this green student over here. Now let's think about the signs of what the signs of the coordinates ought to be. The x-coordinate of this position vector ought to be positive because we went in the plus x direction. The z-coordinate ought to be positive because we're going in the plus z direction, but the y-coordinate should still be negative because we're still going down from the origin. And so it's plausible that these, down at the bottom, it's actually printing out the coordinates. It's 3.5 is the x plus x direction, minus 0.7 in the y direction, and 4 meters in the z direction. That's a pretty technical question, Seth. I've written this program so that I have to click on an object to, and this, let me say that this is an example of the kind of programming you are not going to do. You are not going to write user interfaces. The code for this program happens to have a very small amount of code to generate these objects and a huge amount of code for the user interface, and that's completely irrelevant to what we're going to be doing. So if you're interested in that, that you can do on your own time, but this is not what we're doing. And now, but we can also find a position of something relative to something that isn't the origin. So we could start an arrow at the instructor, and we could draw it going to this green student. And now the tail of the green vector is at the location of the instructor. The vector this arrow represents is 5.50, 5.5. We went 5.5 meters in the x direction, 0 meters in the y direction, and 5.5 meters in the plus z direction. And you can see that these three arrows define a plane, actually. Okay, good guess, Dylan. So the magnitude of a vector is, in fact, a magnitude is the size of the vector. And so that, in this case, for position, when a vector represents a position, then that's the distance the vector extends. So it is indeed the distance from the instructor to the student, and we're about to learn how to calculate those things. So let's, I'm going to take a screenshot of this. So let's look in a little more detail at what we've done with vectors here. Let's see, I might want to make this object a little bit larger so that we can write on it. Okay, so we have these three, we've drawn these three vectors here. We have a red vector. We have a blue vector. It doesn't look super blue, does it? And we have a green vector. Typically, when we write position vectors, we often use the symbol R for a position. So, and when we write a vector, what's a vector? Well, a vector has three pieces, three coordinates, X, Y, and Z, right? So typically when we write a vector, we're going to write a symbol with an arrow over it. And I'm going to call this one, typically we're going to be calling things like R1 and R2, but I'm going to call it R red. I'll call this one R green, and I'll call this one R blue. And vectors have their own rules of algebra, rules of math. Some of them are like the rules you know for ordinary numbers, and so we're going to call these are vectors, and they have the form x, y, z. A single number is a scalar, like one number, so 5 is a scalar. And we can do various things with vectors. We can add them and subtract them, for example. So in this case, if we think of a journey made by, say, a moth, which started at the origin and flew to the top of the instructor's head, and then it flew to the top of the green student's head. We could say that first the moth did this, R red, and then it went this way, R green. So its total displacement from where it started is there, and this is actually the sum of R red plus R green. So let's see how that works out numerically. So the red vector was -2, -0.7, -1.5 meters. And the green vector was 5.5. Whoops, let's make that a little cleaner. 5.50, 5.5 meters. And if we add these two things together, -2 plus 5.5 is going to give us 3.5. So we're adding the x components here. And now we're going to add the y components. So a -0.7 plus 0 gives us a -0.7. And we're going to add the z components. A -1.5 plus 5.5 should give us 4 meters. So this is R red plus R green. And in fact, that actually does give us the coordinates of this blue vector, which we see here. R blue is 3.5, -7.4. Okay, Emily, that's a good guess. We'll see that it's not quite right. Okay, so the displacement is the total distance from the starting point. The distance is how far it traveled, but we're going to see it's not the sum of the magnitudes, which is a very interesting thing about vectors and an important thing to note. So let's get there in a second. So our blue is 3.5, -0.74 meters. So we have our first vector equation, which is R blue is R red plus R green. So that's the total displacement. Now, looking at this diagram, so if we guess that vector algebra is like ordinary algebra, we could actually rearrange this to say, suppose we subtract R red from both sides. So we get R blue minus R red is our green. Is that correct? Well, it actually is, and it shows us something important about graphically subtracting vectors and graphically adding vectors. So when we add vectors graphically, we put the tail of the second vector at the tip of the first vector. So we had, up here we have the tail of the green vector at the tip of the red vector up here. And the sum goes from the tail of the red to the tip of the green. We subtract vectors, we add vectors, so R1, R2, R3, drawn kind of sloppily. Let's draw it better here. R3. So we put R2, we moved R2 to the tip of R1, and to subtract vectors, we put them at tail to tail and draw the final vector. The resultant goes from tip of the initial vector to the tip of the final vector. And so we can see from our diagram up here that we have the green vector in this diagram here. The green vector goes from the tip of the red vector to the tail of the blue vector, so green must be blue minus red. And again, mathematically, we just do it by subtracting vector components. Oops, let's write in black. Okay, does this mean that the V2 minus V1 is opposite in magnitude to V1 minus V2? It's not opposite in magnitude, but it is opposite in direction. So let's see how this works. We have R1, R2. This vector here would be R2 minus R1, whereas if we have R1, R2, that vector there would be R1 minus R2, so final minus initial. So the length of the vector is the same, but the direction is opposite, which means that it's important to get our subtraction in the right order. So what were we subtracting up here? We were subtracting our blue minus our red. So this vector was the green vector, negative 5.50, 5.5. But if we drew it the other way, then the vector would in fact be R1 minus R2 is going to be equal to a negative 5.5 because it's going in the negative x direction, nothing in the y direction, and a negative 5.5 in the z direction. Well, the displacement from the origin is just given by the original position vector, right, Marco? So if we look up here at the diagram, this red vector gave us the position of the instructor relative to the origin. And the blue vector gave us the position of the green student relative to the origin. What the green vector gives us is the position of the green student relative to the instructor. So subtraction gives us a relative position to something else. I mean, it does reduce to, it would be the same for the origin, because we could say that this is a position vector relative to the origin. So this would be this location of the green student, -2, sorry, it would be it would be 3.5 minus 0.74, and it's relative to the origin, so that's that minus 0, 0, 0. So a relative position vector relative to the origin, you're always subtracting 0, 0, 0. Now, you've been asking a lot of questions about magnitude. So magnitude. So how do we get the length of one of these vectors here? Yeah, so if we drew a vector that just went in one direction, that's not very visible. Let's see, let's try this one. Suppose we drew a vector that just went from one student to the next student over to the right here, represented by this cyan arrow. The students are 2.5 meters apart. So this vector would just be 2.500 meters. And that's exactly right, Melinda. It's the Pythagorean theorem, but it's going to be a Pythagorean theorem in 3 dimensions, isn't it? So so the magnitude of a vector, how do we write it? Well, we write it with an absolute value sign, but in the case of vectors, it doesn't mean absolute value. That only means that for a scalar. What it means is we're going to apply the Pythagorean theorem. So we're going to take the square of the x component plus the square of the y component plus the square of the z component. And that's going to give us the distance. So, so let's take one of our vectors here. It says, let's take the red vector, which was negative 2, negative 0.7, negative 1.5. So the magnitude of this vector is going to be equal to the square root of negative 2 meters squared. This is meters, I better be writing units. Plus a negative 0.7 squared plus a negative 1.5 squared meters. And if we work this out, which the computer has cleverly done for us, we find that this comes out to 2.6 meters. Let's see if this looks like it makes sense. This is the red vector, and it's going from the origin to the instructor, and it's a little hard to tell from the perspective, but it looks like that's a plausible length of it, because the distance between students is 2.5. Is the magnitude always positive? Okay, so that's an interesting question. And let's see. Okay, so here's a poll. Can the magnitude of a vector be negative? So the majority is correct here. Majority is correct. Those of you who said no. And why is that? Well, that is because what we're doing is taking the square root of the sum of squares. And so we're always going to be taking the square root of a positive number. And so the magnitude of a vector is definitely going to be positive. Now, in physics, vectors tend to represent physical quantities. So what would it mean to have a negative distance? Okay, it doesn't have a meaning. We could have a displacement that has negative components, but a distance is a positive thing. If you walk 10 meters, you've walked 10 meters no matter what direction you were walking. So it makes sense that the magnitude, well, even if you walk backwards, you've probably still walked 10 meters, haven't you? So I think that it's now, can I explain the difference between a vector's size and magnitude if there is one? In a certain sense, magnitude is just a fancy word for size. So when we're talking about position vectors and displacement vectors here, what the magnitude of a vector is distance. Okay, so it's size. Vectors can represent other quantities, though. So, for example, velocity tells how fast you're going, but it also tells what direction you're going in. And so velocity is a vector, and it could have an x direct component, a y component, and a z component. Our bouncing ball was moving both in the x direction and in the y direction, so it had x and y components. The magnitude of that vector, in a sense, it's the size of the velocity, but really we have another word for it. We just call it the speed. So speed is the magnitude of the velocity vector. Now, can we add magnitudes? Well, let's look at what we've got here. We saw that up here, the blue vector was the sum of the red vector and the green vector. So is the sum of them, so let's ask the question, does the magnitude of R1 plus R2 equal the magnitude of R1 plus the magnitude of R2? So that's the question we're trying to figure out. So let's see how this worked up here. We say that the blue vector, we had R blue was the sum of R red plus R green. The magnitude of the blue vector was 5.36 meters. The magnitude of the red vector was 2.60. And the magnitude of the green vector was 7.78. So it's pretty clear that the magnitude of the blue vector did not equal the magnitude of the red vector plus the magnitude of the green vector. And let's go back and look at our picture here. Actually, to really see this, we should probably switch and go back and look at the original program here so that we can just get a better view of it. So let's look here. Okay, the green vector here is the sum of the blue vector is the sum of the red vector plus the green vector. But we can see that the length of the blue vector is much shorter than the length of the green vector, let alone adding the length of the red vector and the length of the green vector together. So, and it's not, the sum of the magnitudes isn't equal to the magnitude of the sum just because these things are going in different directions. So we went off here to the left, and then we came back over here to the right. And so red plus green equals blue, but the length of the red plus the length of the green is actually going to be a much bigger number than the length of the blue. Okay, we have one more thing we need to establish here. We've got vectors and we've got magnitudes. Let's see. I think we have time for this. We've got vectors and we've got magnitudes. How would we make a vector twice as long as another vector? Suppose we have a vector R1, which is 1, 2, 3 meters. To make a vector twice as long, we could multiply by a scalar. And so that gives us 2 times this vector 1, 2, 3. That should make it twice as long. This is a scalar. And the way we do that is just we multiply each component. So we would get 2 times 1, 2 times 2, 2 times 3 meters, which would give us a vector that was 2, 4, 6 meters long. So this is called scalar multiplication. We can multiply a vector by a scalar. We can, of course, multiply by a scalar that's smaller than 1, which is the same as dividing by 1. So if we had, the same as division. So R1 divided by 2 would be the same as a half times 1, 2, 3, which would be 0.5, 1, 1.5 meters. So we can multiply by scalars. There's some things we can't do. We cannot divide by a vector. That operation is undefined. We can divide by a scalar, but not a vector. And the ordinary kind of multiplication also is not defined. We'll see later on in the course that there are a couple different ways to combine vectors that are called products, neither of which is the same as some ordinary multiplication operation. For right now, though, we have one other thing to think about. So the magnitude gives us the size of the thing. Is there something that just gives us direction? Because it would be nice to say, I want a vector of magnitude 7. So I want a vector of magnitude 7 in a particular direction, say in the x direction. We want a vector of magnitude 7 in plus x direction. You can divide a vector by a scalar. You cannot divide anything by, you can't have a vector in the denominator. Okay, no vectors in the denominator. If you find yourself writing a vector in the denominator, think again. And almost everybody trips over that at some point. So, but keep it in mind. So we want a vector of magnitude 7 in the x direction. Well, here's our magnitude 7. Is there a vector we could multiply it by to get the vector of magnitude 7 in the x direction? Well, suppose we multiplied this magnitude 7 by the vector 1, 0, 0. That would give us a vector 7, 0, 0 meters. And so the special thing about this vector is its magnitude is 1. Because the square root of 1 squared plus 0 squared plus 0 squared equals 1. So a vector with magnitude 1 is called a unit vector. And there's some special ones. So there's one that points along the x-axis, and sometimes that's called I hat. There's a vector that points along the y-axis of magnitude 1, and that's called j hat. And there's a vector of magnitude 1 along the z-axis. It's called k hat. But there's others. You can have a vector in any direction that has magnitude 1. So how would we get a unit vector in some arbitrary direction? Well, suppose our vector r is our friend 1, 2, 3 meters. And we want a unit vector r hat. So anything with a hat, a unit vector has a hat. So r hat. Well, we could just divide the vector r by the magnitude of the vector r, and that would give us a unit vector. So we're going to take 1, 2, 3. We're going to divide by the magnitude of this vector, 1 squared plus 2 squared plus 3 squared. And this is, let's say it's a position vector, so these are meters. And so we get 1, 2, 3 meters divided by 3.74 meters is what that comes out to. And so that comes out to 0.267, 0.534, 0.802. And notice that the units of meters actually cancel, so a unit vector has no units. Class ends at 12:20, but we have 6 minutes. So a vector of magnitude 7 in this direction, so 7 times r hat would be 7 times 0.0267, 7 times 0.0534, 7 times 0.802. That's exactly right, Emily. A unit vector is any vector with magnitude 1, not those special 3 that lie along the axes. I mean, those are examples of unit vectors. So we can write any vector. So factoring a vector, we can write any vector, let's call it A, as a product of the magnitude of A times a unit vector in the direction of A called A hat. So okay. What questions do you have about this piece? Okay, Marco, that's a great question. Can you add a scalar to a vector? And the answer is no, you can't add a scalar to a vector because we're adding two different kinds of things. So no, that's not defined. So what we have are vector operations. We have addition. We have subtraction. We have scalar multiplication. So n times c. We can find the magnitude of a vector d is the square root of dx squared plus dy squared plus dz squared. And we have the unit vector in the direction of d, which is the vector d divided by the magnitude of d. Yeah, I'm sorry if you're having Zoom problems. Another reason for recording these. Okay. We don't have time to do one other thing, which is to talk about how you can get a unit vector from angles. That is in the book. That may be in the recitation, the plan for recitation, but I'll talk to the TAs and make sure we don't end up doing that. What the hat means is just a unit vector. So what the hat means is a vector of magnitude 1. Okay, from now on, we're going to do these lectures without webcams, which I think will possibly help because it'll decrease the bandwidth. If you're in the remote recitation, you're going to need a webcam, but there are going to be a lot fewer people. Okay, so the recording will be up probably late tonight, but you can get at it. This is chapter 1, okay? It's section 1.4, I think, in the textbook. Okay, thanks very much for your attention. You've been asking great questions. I'm very happy with that. And we'll pick this up on Thursday when we'll be talking about velocity as a vector.